Hi folks, and welcome to my YouTube channel, and in this video we are going to look at the Smith's tacho, which is fitted in a lot of old British sports cars like the MG and the Triumph and possibly some other vehicles. The video is going to be quite long. I have it broken up in two parts. A part one, which is a technical part where we're going to be looking at all the technical aspects of the tacho, and then we have a part two where we actually are doing a out-of-car adjustment or calibration on a tacho, which is designed for a 4-cylinder, but we are going to adjust it for an 8-cylinder engine. Depending what you're interested in, you can skip this video and go straight to part number 2, or you can watch this part, which is part number 1. So in part number 1, we're going to do a couple of things, guys. First of all, we're going to talk a bit about the tacho, the different types that exist. Then we'll have a look on the vehicle, on the pulses on the ignition, so we have a good understanding what the input signals are to a tacho. Then we'll open up a tacho like this one and look at the inside. We look at the schematics. I will explain the schematics on how well that works. And then finally, we'll do some measurements and you'll see how we do that. And then in part 2, of course, we do all the practical stuff on how you can modify the tacho and so on if you need to do so. So let's start without any further ado, because we have a lot of things to talk about. And I'm so sorry if I talk too much, but I'm one of those guys that don't believe in monkey see, monkey do. I like to understand what I'm doing, and I guess most of you will be the same, otherwise you wouldn't be watching this video. Right, so the Smith's tacho, as I said before, is a very standard tacho which is fitted into a lot of the old British sports cars, and they come either as 4-cylinder tachos, 6-cylinder tachos, and 8-cylinder tachos. Not tacos, that's something else, that's something to eat. And I don't like it anyway, tacho. Anyhow, I'm just kidding, guys. Over the time, the Smith's tacho evolved. The very first ones were mechanical types, driven by a cable. Now, I'm not going to talk about those because there is little I can adjust on those. It's all mechanical and gears, and I don't even have one. A little bit later, the Smiths came up with what we call the induction-based tacho. And this is a induction-based tacho that I have right here. And it is a special mechanism on how the tacho picks up the pulses from the ignition system, and I'll explain that to you in a few minutes. Later on, this tacho, which is identified, by the way, as RVI, and the I stands for indirect, and if you look closely on the dial on your own or on this one, then you will see RVI, and if you see the I, you know it's an inductive type, and then there's a number behind it. Later, the inductive type went away and they moved on to what we call a direct-driven tacho. And a direct-driven tacho picks up the signal from the ignition coil and it goes straight into the tacho itself. And I have one over here which is a very new one now. In fact, it's a brand new one for an 8-cylinder, but that's a direct-driven tacho. So all of them are electronic tachos, but they differ a bit. Now, even the RVI, the inductive type, inside there are different approaches to that. Of course, technology evolved. The very early ones had 2 transistors inside, working with a monostable vibrator. Later on, they became 1, and then even more later, they started to using a chip, and then at the end, they removed actually the inductive coil on it, and we ended up on where we are now, which now we have standard modern tacho, which you can really adjust or program. But in between, there are some variants. But the functionality is still the same, at least on the RVs, the RVCs, and the RVIs. So before we start explaining all the technical details of this RVI tacho, because I'm going to start with this one, we are going to look at the real pulses on a vehicle. How do they look like? Because I believe it's important to understand how an ignition pulse looks like. And then we can actually simulate those here on the bench and then start working on the tacho. If you look closely on the dial, then you have seen that there is a marking there and it says positive earth. And that's because the vehicle where this tacho comes out from had the positive side of the battery connected to the chassis. That's how they used to do it in the old days, and it's a bit British, I would say. But okay, that's what it is. Later on, they changed it and it went to a negative earth. So if you have a tacho or you're buying a second-hand tacho, make sure that the tacho fits your car, that you have a positive earth tacho for a positive earth car or a negative earth tacho for a negative earth car. So this MGB is a conversion. Somebody converted it from a 4-cylinder to an 8-cylinder. But what they forgot when they did the conversion is to modify the tacho, because the tacho is a tacho for a 4-cylinder, and obviously if you put an 8-cylinder in the car, you're going to have twice the amount of pulses coming out of the engine per 2 rotations. A normal 4-cylinder has 4 pulses of ignition per 2 rotations because it's a 4-stroke engine, right? So it's intake, compression, labor, and exhaust. So that's 2 full rotations, and we have 4 times ignition in one of each of the cylinders. It happens once. So if you're putting an 8-cylinder in, then that's going to happen 8 times. In other words, the tacho is going to indicate an RPM rate which is way higher than it actually is on your 8-cylinder. So if you watch the tacho, you can see that it's actually around 1,000 RPMs. But if I give some throttle, you will see how funny it's going to act up. See? So the RPM meter is doing all kind of funny things. It flips back and forth and it's not showing the right RPMs. So we need to calibrate this and correct this. So the point now is that we don't know how much RPMs this engine is running. So we can check this with a normal tacho, a test tool. Or if you have a strobe light with a tacho on, you can check it out. But I'm going to do it a bit different because I want to show you the ignition pulses. I want to make them visible so you can actually see it, because then you will understand how the tacho is working and how you can calibrate it. So for that purpose, I'm going to use an oscilloscope. Now this is a small handheld one. That's a bigger one. This is about 40-50 euros. So guys, this is a little handheld scope. Cheap and very handy if you work on cars. It works for all kind of things. So I really recommend that you buy something like this. You don't have to, of course, but this is really handy. This is about 200 euros. It's up to you if you want to buy this or not. I use it for all kind of other purposes. But with that, we can visualize the pulses, we can measure the time in between the pulses, and then we can use all that information for our effort that we're going to do in the lab in a few minutes to adjust and calibrate the tacho. So I'm going to hook up the scope, and we have ground, and connect the probe to the positive side of the coil. So the positive side is where the power lead comes in from your ignition. All right, guys, the scope is hooked up, and you can see that right now we have no signal whatsoever. So I'm going to crank up the car, and then we'll see what happens. When I cranked up the car, you can see immediately all the pulses, and these pulses are the ignition pulses. If I make the engine to run faster, you can see how these pulses are getting closer to each other, and the slower the engine is running, the further away they are from each other. I put up my strobe light, and we can look on the tacho right here what the current RPMs are. They're going up and down a little bit because the engine is still cold. But I'm going to capture this, and I will look at the same time on the oscilloscope, but the time is over there. So I have the engine now running at around 650 RPMs. So I'm going to capture it on the scope. And now we have the trace captured. So these are the ignition pulses, and I'm just going to put the cursors up. So it's spot on. I would say it is 22 milliseconds in between 2 pulses. So now let's see if we can figure out how many RPMs that is. And it better matches up the RPM meter that we have hooked up. You've seen on the oscilloscope that we measured the time in between 2 ignition moments to be 22 milliseconds. 22 milliseconds multiplied by 4 pulses gives me 88 milliseconds for 4 pulses. Now, why is it 4 pulses? Well, we know that a 4-stroke engine does 2 full rotations to complete a intake, compression, labor, and exhaust cycle. So we have an 8-cylinder, so normally we would have 8 pulses. So I just divided it by 2, so we know that 8 pulses are 2 rotations, 4 pulses are 1 rotation. If this was a 4-cylinder, then that would be different. Then that would be 2 pulses per rotation and 4 pulses per 2 rotations. But this is an 8-cylinder, so this is what we're going to do. So I guess you can agree with me so far that that's what it is. So if we now divide 1 by 0.088, because that is in milliseconds, then we know how long it takes for the crankshaft to do 1 rotation. Now I already worked it out because I didn't want to do it here on this paper because it would take too long. It boils down to about 11 rotations per second. So that division, 1 divided by 0.088, gives me 11 rotations per second. If I multiply this by 60, I get 660 rotations per minute. And that is what we measured with the tacho. I know I did say 650. It just jumped at that moment in time to 660. So it went up and down a bit. But now you can see that with an oscilloscope, you can do a very, very accurate measurement. And you probably wonder, why do you need to know all this? Well, it's good to know because we're going to need this to calibrate the tacho in the lab in a few minutes. So let's have a look on the Smith's tacho, the inductive type, on how that all fits together. So on the picture on the right, you see the tacho diagram, and that's the internal stuff. So don't worry about it. We'll be talking about that in a few minutes. But first of all, let's look on how the ignition pulses are being generated and how they are fed into the tacho. Now remember, this is the inductive type. So we've got the contact key right here. So as soon as you turn on the contact, but don't have the engine running yet, 12 volts from the battery through the fuse box will actually be applied over the loop, and this is the wire loop that you've seen in the back of the tacho. If you look close enough, you will see actually over here a coil, and this coil is the pickup coil, the inductive pickup coil. And in the back you see this red cable, which is kind of looped through a back plug here. Well, that's where the induction is going to happen. That's why we call it an inductive type, all the way back to the positive side of your ignition coil, and then it goes through that and it stops. Now, the moment that the breaker points are closed, then current will continue to flow. Now, as soon as current picks up, we'll see a spike happening in the coil, magnetic field changes, and you get a spark happening here. So we would be seeing a spark for every ignition moment, and you've seen it on the oscilloscope. I'm not showing that exactly the same way, but that's how it kind of looks like. The time in between the pulses is determined by how fast the engine is running, but the spike itself is always the same. So if you have an 8-cylinder, you're going to have 8 spikes per 2 full rotations of the crankshaft, and that we have already explained. Now, because the current is flowing through this pickup coil here, the transformer inside the tacho will pick up these pulses, and it will toggle that specific monostable vibrator. So now let's have a look on the second diagram. So let's have a look on this diagram here, and on this side we actually are having the tacho as we've seen before. Then we have here the whole ignition system where we're picking up the pulses, remember, right here. So at this point A, that's this point here. So we get the ignition pulses incoming, one after the other, and the monostable vibrator, which is actually the transistor Q1 and transistor Q2 in combination with the capacitor C2, that's an important one, and the resistors here, and this variable potentiometer. That is your RC ring, and that's going to determine how long the output will stay high. So I could draw it like this. So any incoming pulse would be extended on the output. So that is kind of what a monostable vibrator does. So a single pulse incoming causes a longer and extended pulse at the output. And this is a point number 2, and this is point number 2 in the diagram. And then if that happens, then the meter will actually deflect. Now this is actually the meter system, the little coil and the meter on your dial that will move around. So that's what a monostable vibrator is really doing. Nothing more than that. So an input pulse is converted to a longer extended output pulse. Now if you go into calibrate a Smith's tacho, you are playing with the resistor R5, this resistor right here. And that's done by using a screwdriver, and you turn it left or right, and then you can adjust the deflection of the needle on the display. Now I'm going to show you on how you can do this, because for that you need to know the pulse times that we just measured on the vehicle themselves. Once you know the pulse times, then you can calculate RPMs, and then you can actually adjust R5 until the dial has the right indication. So that's a little bit in a nutshell on how that works. So now let's dig a bit deeper down into the circuit diagram for those of you that are interested in it. So now let's dig in a bit deeper and look at the actual diagram of the tacho. Now the diagram I'm having here is the model with 2 transistors. There's also a model with 1 transistor or a chipset, so that depends a bit on the tacho, but the principle is always the same. It's the principle of a monostable vibrator. And over here you have the 2 transistors, Q1 and Q2, at the pickup coil, and in the back that's where you normally have the looped wire. Now, for those of you that are not familiar with electronic components, I will give you a little indication here. This symbol right here, that's what we call a transistor. So Q1 is a transistor, and it's nothing more than a switch, right? So if the voltage at this point here, which we call the emitter, is equal to the voltage at the base, and we call that the base, then the switch is open. The voltage at the base has to be minus 0.3 volts below the voltage that you would have on the collector. And if that happens, the switch is closing. This is the second transistor. It's the same type. And by the way, these symbols refer to a PNP transistor, just in case you want to know that, because there's also an NPN that exists. So if you look on the transistor, this arrow pointing thing here is what we call the emitter. This side we call the collector, and this place here we call the base. Very simple. Right, this symbol here, C2, is a capacitor. The zing-zang is a resistor, and the zing-zang here with this little arrow is the potentiometer or an adjustable resistor. Over here we got actually the dial. So this is the coil where the needle is on, and that's the dial on your RPM meter. On this side we've got the input transformer, and you've seen that on the video already. This is this little coil, and then this is the wire that we just discussed, which is coming actually from one side is going to your ignition coil, remember, and the other side was coming from your fuse box to provide the 12 volts power supply. So when current was flowing, we saw that pulse, you remember that? Current flows, that is, and then we had these pulses incoming, right? Okay, so let's get back to the diagram. So imagine now that the contact key is turned on. We just turned on the ignition, but we don't run the engine yet. We haven't started it yet. So in that moment in time, the stable condition of this circuitry is that this will be at plus 12 volts. And the base will be at plus 12 volts as well. Why is the base at plus 12 volts? Well, that's because 12 volts is here, and it comes through the coil, and it's applied straight to the base. So a coil does not affect a DC current as such, so the voltage will be the same. Now 12 volts on the base, 12 volt on the emitter, it's the same potential. The transistor is open, no connection. In other words, no current can flow because this point is at 6 volts. and no current can actually flow through the dial, so nothing is indicated. As soon as the ignition is turned on, the first pulse will come in. When the first pulse comes in, it will be picked up by the transformer, and the transformer actually will then drag the 12 volt down. It will drag it down maybe to 11 volts or something like that. It depends a bit on how big that pulse is. And then the transistor will close, the switch will close. So basically, this is what's going to happen. It's just going to close like this. And then the 12 volts is applied at this point. And now we have 6 volts and 12 volts. So now current will flow through the dial, and the dial will deflect. So the needle will go to a certain position. And remember that Q1 and Q2 are forming the monostable vibrator. They will actually cause the output to look like this. Remember? So what comes out here is a longer extended pulse compared to the peak that you got in here. Now the length of that pulse is determined by the value of these resistors and this capacitor. And the wider that pulse is, so let me show you that, like this, and this would be a pulse, this would be an incoming pulse, right? So the wider that is, the more current that will flow through the meter. So the wider or the further the dial will point. The distance between those points, that's determined by the spikes that are coming in from the ignition. So, but the gap here, that's determined by the adjustment of the R5 variable resistor and together with the capacitor. So we could adjust it that it looks like that. So like this. But we can also adjust it that it looks like this. So that's where the trick comes in, because if this is all calibrated for a 4-cylinder vehicle, then you may have a problem if you hook it up to an 8-cylinder one, because remember, the amount of pulses is now going to be the double. And if that's the double, then you will see that these pulses here, there will be more pulses coming in. So at the end, it may be like overlapping, right? And when that happens, then the meter goes really crazy, and you can see that quite often on vehicles that have been converted and they did not adjust the tacho. All right, so that's about it for this, guys. What can go wrong with all this? Well, there's a few areas that can go wrong on this. One of the main problems that you will see over time is this capacitor here, C2. This guy tends to dry up over time. The other problem that you will see is that the transistor Q1 might be bad, or you may have a bad pickup here. That happens sometimes as well. And also the thermistor may lose its value over time. This actually is a compensation for temperature, so if things get warm, it will adjust the resistance. So it's a control or a correction depending on the temperature for the current flow through the actual dial. And that's basically it. So now let's get back to the real thing. I've taken the tacho out of its enclosure and I set it up on the test bench. The clips that you see here, the black one and the red one, this is just the power supply for the tacho. And remember, this one is a positive earth one. If you are running one which is negative earth, then of course you will have to reverse the polarity of those two power leads. But that's not the point I'm trying to make. If you look close enough, you will see actually over here a coil. And this coil is the pickup coil, the inductive pickup coil. And in the back, you see this red cable, which is kind of looped through a back plug here. Well, that's where the induction is going to happen. So this wire is coming from your fuse box. And it's run from your fuse box ignition fuse to the tacho. It loops through, and then the cable goes back out to the positive side of your ignition coil. and of course your ignition coil then connects to your breaker points, and so on. So as soon as your breaker points are closing, then current will start to flow from the battery through the loop and then back down to the ignition coil, through the ignition coil and onwards to the breaker points, and a spark is happening. But as soon as the current starts to flow, a magnetic field will be generated here, and that magnetic field will induce a pulse inside this coil, and then that pulse will drive this transistor, and then the bi will drive this transistor, and the monostable vibrator will then do its job. Furthermore, you can see that this specific tacho is one which is having 2 transistors in it, and we'll talk about those things, so don't worry about it. You also have models with 1 transistor, and you have models with a chip inside. Typically, you don't find the chip on induction-based tachos. And this is the potentiometer that you can adjust with a screwdriver. Not that hard to get to. Now this is already adjusted now. And over here, this is the well-known C2 capacitor. So this capacitor, together with the potentiometer and some other small resistors in between, like that one, are forming the RC circuitry for you. So quite often, that capacitor is faulty and you might have to replace it first because they tend to dry up over time. I rigged up a Smith inductive tacho to the power supply. This is the power supply that's providing power to the RPM meter itself, to the tacho. And then I have another cable running, coming from my battery. This is the red one, going to the back through the loop. You remember the inductive loop, and then back out to my breaker points, and I'm simulating the breaker points right here with a relay. And then it comes back out of that. It goes to this light bulb, and then it goes back to the power supply. So the light bulb is basically my coil, and this little relay here are my breaker points. So that way I can actually simulate what we just did live. And over here I have a signal generator where I can generate a pulse every 22 milliseconds, and I'm feeding that actually to my breaker points, to this relay, so I can actually simulate the points opening and closing. I can't do it straight over the wire for the light bulb because there's not enough power on this thing, so I'm using a relay for that purpose. And with the scope we can actually see the trace. So let me turn on the output and then watch the dial already. It's set to 22 milliseconds. That should be 660 RPM. And let's see how close that is. There we go. So this tacho for 4-cylinder is now showing me around 2,700 RPM, which is way off. So now we need to adjust it and calibrate it so it will indicate actually 660 RPM. Here on the scope you see the waveform, and you see the time in between the two is 22 milliseconds. That's the same thing as the pulse we've seen on the live vehicle. So I'm going to use a little screwdriver to do that. So far we've looked at the pulses on the car. We actually measured them. We know it was 22 milliseconds. We then rigged up the tacho here in the lab with the simulation with the light bulb, which was supposed to be our ignition coil and a reed relay, so we could act and pretend to be breaker points. We run it through and you could see how the dial was working, but it was a bit erratic. It was not 100%, and that's because the current through the wire for this light bulb isn't enough. On a real car, there's a lot more current flowing through your ignition coil. So that's why that's not an accurate method to do it. The better method is to use your signal generator again, set up the right timing as we already calculated, and then plug in the signal which is coming out of the signal generator straight into the base of transistor Q1. In other words, immediately after the pickup coil that we have in this inductive tacho. If you're going to inject the pulse into the system, then make sure you do it behind the pickup coil, the lead that is going straight to the base of this transistor Q1. And that's actually on this capacitor right here. That's where you should clip it on, and then it should work. Now the pulse itself, you're good if it's about 3 volts. It should just do the trick for you. And that will be a lot better, and we are going to represent pulses. So I've set up the pulses right now to 22 milliseconds, which is exactly what we had measured on the vehicle. And actually you can see the pulses in here, and if they were to lock one time, see how they lock, it is actually 22 milliseconds. So that's the good thing. You can see that the tacho is indicating around 1500 RPM. So now we can adjust it. So let me try that. And we know that 22 milliseconds is exactly 660 RPM. So let's do that. Hopefully I don't get too much in the way, guys, because it's not easy to get to it without being in the way of the camera. But let me turn the potentiometer and see how we can actually adjust this. So now you see how this is a lot more smoother. So now we can adjust it to the minimum we can get it. And there we go. A little bit more, and then we should be about at the right place, I would say. 660 RPMs. All right, so there we go. So the next step is that we're going to increase the RPMs, and we're doing this by reducing the time. So the closer the time becomes, the faster the engine will run. So if I halve the time in between the process of the ignition, which is now 22 milliseconds to 11 milliseconds, then we should have far more RPMs indicated on the dial. So let's see if that is going to be true or not. So let me turn off the output. I'm going to dial in 11 milliseconds. That's done. So let's send it out and see. Well, look at that. Now I have 1200 RPMs. Isn't that good? And you can actually see it on the scope now that we have double the pulses. And this is how you can do this. Now you cannot calibrate the meter at different RPMs. You have to do it at a specific one. I probably would calibrate it around 4000. I think that's probably the better scale. But let's see if we dial in another number again and make it even smaller. So we have to double again. So we go for 2 milliseconds. And let's see what happens. Wow, now with 2 milliseconds, I'm way in the red, right? Now 2 milliseconds, that is a tenth, 1/10 of what we had before, and a tenth or 10 times the RPM. So this is 6,000, about 60. So this is pretty accurate. So I am quite sure that this is now working properly. So let me go back to 22, and we're falling back to 660 RPMs. I'm going to try to let it sweep so you can see it cranking up. So far we adjusted or calibrated this inductive 4-cylinder tacho from Smith for an 8-cylinder behavior, and now that is looking quite good. We've done it now calibrated directly onto the circuitry, which is different than going it through the pickup lead. And I have now set up a sweep, so it's going to be like, you know, you're pushing down the throttle and it's going to go to maximum RPM, and then it's going to fall back, and that should work quite smoothly. So what's the pulses here? In the beginning they will be far apart from each other, but after a while they're going to get closer and closer, and that's quite normal because the RPMs are increasing, and that's how it would work on the car. So let's have a look. You see how it's cranking up and how these pulses get closer and closer? There we go. And now it's going to drop down and it will start all over again. And this is how it works. All right. And you might wonder if this is accurate, but I believe it is. But let's test it out. I'm going to let the sweep go, and when the meter indicates around 4,000 RPMs, I'm going to capture that signal on the scope, and then we can measure it afterwards. So let's go and do it. Are we getting near? Okay, I should have it. So here is a trace, and let's measure the time in between pulses. So first of all, I'm going to scale it up a bit so I have a better reading. And that's exactly 3 milliseconds. You see that right there? So I'm going to call it 3 milliseconds. Let's see how accurate that was. So we had 4,000 RPMs when we captured the signal. And the timing at that moment in time was about, and I just double checked it, 3.1 and 20 milliseconds of the waveform. Now we know that 22 milliseconds equals to 660 RPM. So now it's an easy division. You just divide it, and then we know, so 22 divided by 3.20. So if we divide this, that is probably going to be about 7 times. So that will make, basically, we're talking about 7 times. So 3.1 millisecond is about 7 times faster, roughly, than 22 milliseconds. So 660 RPM multiplied by 7, that's about 4,620. Now, obviously, I am not sure if I captured it exactly at the right time, but you can see that this is matching up pretty well. The tachos that have an adjustable potentiometer may or may not have a hole in the back of the enclosure to get to it. So this one has it, so I could actually get in and adjust it. But they don't all have it. So if you don't have it, then you will have to take the enclosure off, maybe drill a hole where it is, or leave it out of its enclosure and then adjust it. In all cases, you have to remove the tacho from the vehicle. You cannot do it in vehicle. That's not possible. So folks, we are nearing the end of this video. You've seen on how we adjust the tacho. We've done it in 2 methods. I rigged it up once and simulated the ignition coil with a light bulb. That is not the way to do it, but I wanted to demonstrate it to you on how the inductive tacho works and how it does pick up the pulses. And then we did an actual adjustment by injecting the proper timing signal into the tacho itself and then adjusted the potentiometer. In my next video, we are going to do this live on the vehicle without a real signal generator. We'll do it a bit different, and we also will install a direct injected tacho and adjust it on the vehicle. So I hope you enjoyed it, and please provide me back with any possible comments if you do have any, because I'm always willing to learn from you. Thank you and have a great day.